This computer. Okay, hello everyone. Welcome back to the ARC seminar. So this is the first one of the term, and it's being given by me, which is great. So I can also be the organizer. And I wanted to sort of go through a whirlwind tour of a kind of object called white dwarfs. And first of all, I think white dwarfs are cool. And second of all, many of the people that typically come to this event, and also I guess of order half or more of the people typically think about relativity. And then so they think that white dwarfs are like kind of the least interesting compact object that exists out of, white dwarfs, neutron stars, black holes. And so what I want to do was kind of motivate kind of like do a whirlwind tour through all of the different kind of research topics that I could think of that exist in white dwarf physics, to give you kind of an idea of the diversity of study in this field. And it's not exhaustive, and I'm more familiar, more and less familiar with certain different topics here. So um, I may or may not be able to answer questions to your satisfaction based off of what topic it is. Okay, but we can also, I should say, like, because I try to cram as much stuff in here as possible, I don't know how long it's going to take. And so some things may need to be cut. And also, it will probably be like the slides will be very packed. So if in doubt, like just listen to what I'm saying because it's more like an aid for what should come out of my mouth. So first, what is a white dwarf? So first of all, it's a compact object, so it's basically the outcome of most stars, right? So of course, stars can blow up, they can become neutron stars, they can direct collapse to black holes, but 95% of stars are not massive enough to do that, and they just become white dwarfs. And white dwarfs are basically kind of degeneracy supported objects. So they're basically like stars in the sense that they're in hydrostatic equilibrium, but they're electron degenerate. That means they're actually held up mostly by electron degeneracy pressure, which scales in this way. It's rho to the 5/3. One can kind of show this. And the crucial point is, unlike something like the ideal gas law, this has no dependence on temperature, right? So in the limit of zero temperature, there's still pressure support, right? So even if you have a white dwarf, which is at absolute zero, it still has pressure support. And so unlike a normal star, fusion is like not necessary, not like a big part of holding them up. And so yeah, and they come from stars. And then here are some other properties about them. So just like, there are a diverse class of objects, or quite a diverse class of objects, but just to give you an idea, you should be imagining something which is of order a solar mass, maybe a little bit more, maybe a little bit less, and something which is of the order of of an Earth radius, right? So quite a compact object, maybe not compact enough for people here to be satisfied. And one crucial property is it turns out that more massive white dwarfs are actually smaller. Okay, so it actually scales a little bit weakly, but still kind of importantly, R goes as m to the minus a third. And as a result, that translates to white dwarfs, which are more massive, being dimmer, right? And their surface gravities are naturally very big. Mesa will define like the uh, beginning of the white dwarf stage as log g of 6, but can go all the way up to 9 for like the pretty massive white dwarf, so maybe a little bit more than that. And that is, by the way, like the log base 10 of the surface gravity in centimeters per second squared. Okay, so this is just like a astronomer thing. We call this log g. And yes. And please interrupt me, by the way.
So what is the temperature required that we should take into account several effects? Like one, like same question
Mhm.
is, what's the Fermi energy typical of light?
That's a good question. I'm not entirely sure, but that is the criterion, right? So the thermal energy competing with the Fermi energy. I don't know, to be honest. Um, yeah, but I mean but the temperature, it's clearly not just a function of temperature, right? Because these things they can have T effectives which are very like hundreds of thousands of Kelvin or tens of thousands of Kelvin.
And they're still white dwarfs.
They're still white dwarfs because they're dense, right? So
Yeah.
so they're like this is like an alternate branch of uh alternate branch of the stellar solution, which can still be hot but is like not supported on a different branch of the EOS, right?
But you can always make compact stars to by increasing their own water. So like use it.
Yeah, that's true. I don't have a sense actually. Yeah, I'm not super sure. Um, yeah. Also, the difference is not just that, but it's also whether you've heated it up enough that you can like start burning, right? So like then if okay, anyways.
Yeah.
So one thing I want to make a point about this. White dwarfs seem like, pretty boring objects in the sense they just kind of sit there and they cool into space, but they're pretty diverse objects. The least massive white dwarfs that we know of are approximately like maybe like 0.15 solar masses or so, right? And then the most massive are like pretty close to the Chandrasekhar limit. And so on either end of this, the radius mass relation is going to be modified. But let's just say that it holds just to make this point. So you can work out that rho is, m over r cubed, which is basically m squared. And then that basically means that the least massive white dwarfs and most massive white dwarfs are like basically 2 orders of magnitude different in density, right? So these are very different objects you should be imagining. And then there are also, it turns out that there's a mass set by special relativistic effects, where like, which is basically sets a maximum mass for white dwarfs, which is called the Chandrasekhar limit, and it's about 1.4 solar masses. Okay, so that's a pretty important thing. Um, it turns out that the bulk of a white dwarf is essentially isothermal, because the transport is so both thermal and electrical conduction are very high, and they're mediated by electron conduction. So not something like radiative diffusion like you might be used to in a normal star, or like not like you most of the star isn't convective. And as a result, the interior of the star is basically one temperature, and the cooling is regulated by the envelope, which is non-degenerate and has a higher opacity. Right. So basically, the entire interior of the star is one temperature, and then like there's like a kind of blanket on top of the white dwarf that's regulating how fast it can cool. And these stars, they're not burning any element in any substantial amount usually. And so their abundances are not changing that much. They're maybe mixing around or settling or some stuff like this. But their primary kind of evolution is just cooling. Like literally, you have a ball, and it's just like cooling due to black body radiation over the course of the universe. And like I will say for now, like not doing much else that's interesting, but there is some stuff that happens.
Are they
Um,
cool? Do they get bigger or smaller? About the
they
same?
get slightly smaller, but like not that much smaller, like a little bit smaller. And also, even like one thing to point out is even though they're supported by electron degeneracy, their ions are not degenerate like they would be in a neutron star. I know that's a simplification, but as a result, when you calculate like their heat capacity is dominated by the ions, right? It doesn't have much to do with the electrons, right? And so here's just like a snapshot from Shapiro and Tucholsky's book, black holes, white dwarfs, neutron stars, and so you can derive somehow this scaling for the cooling time scale. Um, Also, like one thing that I want to point out, which is a little bit random, is that oftentimes you can detect white dwarfs, even though white dwarfs are pretty dim because they're very small. Sometimes they're very hot, and so you can take a spectral energy diagram and like look at a star in like different frequencies, and you can see like a sort of like blue hump corresponding to the white dwarf, and so in that way you can oftentimes find white dwarfs even if like they're outshone by a star. But note that it's not always possible because white dwarf's cool, and if the white dwarf is cooler than the star or like of comparable temperature, it's like a lot dimmer, and then you can't find it. Um, and so like white dwarfs can have a lot of temperatures, but I think the coolest I looked this up, and like the coolest that's been discovered to my knowledge is like 3,000 Kelvin, right? So the sun is like 6,000, right? So they don't actually have to. So they start off hot, but they don't actually have to be hot, and also they cool, like in the sense of like the verb, like to cool over time. Um, so this is really an elaborate trap to trick you into learning stellar evolution. So white dwarfs come from stellar evolution, so I will just briefly talk a little bit about it. On the left is basically what our sun is doing and will do. And on the right is like a more massive star, maybe like 5 solar masses. And they kind of have similar evolution. They look a little bit different. But basically, there are 3 sorts of white dwarfs that you should care about, and you can sort of see how they would come out. And we can just focus on the left panel because they're kind of similar. So the sun is originally a ball of hydrogen. It burns through the hydrogen in its core, and eventually it accumulates helium in the core. And that helium is for a 1 solar mass star is degenerate, right? So the star basically is like burning hydrogen around this helium core, and the helium core is growing in mass over time. And as it's growing in mass, the star, can you see this mouse? The star basically ascends the red giant branch. Okay. So here's the first place where you can make a white dwarf. If you have something which either strips the envelope, which basically strips the envelope off of the red giant, either you have a common envelope event or you have stable mass transfer, you end up with a helium white dwarf. A helium, sometimes it's called a helium core white dwarf to make it clear, like you're not talking about the atmosphere only. And basically the mass of this helium white dwarf is set by like when you truncated the red giant branch, right? And so it turns out the core starts off, basically at 0, and then at the tip of the red giant branch, it's a little bit less than half a solar mass typically. And so this is the first kind of white dwarf. It's called a helium white dwarf. 0.15 to 0.5 is roughly the mass range. Stars which are lower mass than like about or like quite lower mass than the like M dwarfs, like in principle they should evolve into helium white dwarfs by themselves, but like those things have such long lifetimes that the universe is not old enough for them to have died. So every helium white dwarf in the universe is made by binary evolution. Okay. Great. And then after this, you get to the tip of the red giant branch, and the helium itself ignites. Yes.
Are helium core?
Yeah.
A white dwarf?
Yes.
Always?
No. Well, what do you mean, sorry? So there are non-degenerate helium stars as well. So it turns out also one point which I'm not going to talk so much about, but if I do a common envelope event very close to the tip of the RGB, I can also get a stably burning helium main sequence star called an SDB.
So we need sun there. Helium is piling up near the center.
Yeah.
It's not hot enough to burn helium.
Yeah, right.
But this helium piling over.
Yeah. Yes. For stars which are less than 2 solar masses, it's degenerate.
So that's basically white dwarf piling up.
Yes, yeah. So a red giant is basically a white dwarf with burning on top of it. Conceptually. Yeah. So yeah, that's a good point. Yes, just keep that in mind. You start to burn helium. You kind of burn helium first. Like basically the core is behaving as if it's a helium star. There's an envelope on top of it. And then eventually you run out of helium in the core, and then you start burning helium in a shell. And then you burn all of that helium into carbon. It turns out there's also this other reaction that happens at the same time, which turns carbon into oxygen. But it is actually, that reaction rate's not known to like 10 or 20% maybe. And so then you end up with a phase up here called the asymptotic giant branch, right? And the phase I'm most talking about is like kind of like the thermally pulsating asymptotic giant branch. But basically, one thing I want to say is as a result of us not knowing this reaction rate very well, we don't know the fraction of carbon and oxygen in a carbon-oxygen white dwarf. So it's typical to assume 50-50. I think like in MESA, like more of the core becomes oxygen than carbon actually, but it's some mixture between these. Okay. And at this point, either you can have a common envelope up here or some stripping up here. That's possible. Or more likely you have like basically thermal pulses that kind of kick off the hydrogen envelope, and then you end up with a carbon-oxygen white dwarf. So these are like the kind of prototypical white dwarf you should think of, and they're made by single star evolution. Yeah.
Maybe a bit of a tangent, but I was going to ask, like, do you know how those like heavy element fusion reactions are measured? Like,
I don't know, but I think there's some experimentalists can do it on Earth.
Oh.
But I guess like maybe there's some uncertainties that prevent them from.
Okay,
Yeah.
I was wondering if like 20% is like considered very uncertain in like the field of like deep like heavy element.
I mean I think other reactions like, for example, in hydrogen burning, like the PP chain or CNO cycle are known better.
Yeah.
Yeah, but like this particular one is like notorious for not being known that well. So then, carbon oxygen white dwarfs, they are produced by, stars which are like somewhere like sun size to like maybe like, I'm not sure the exact number, maybe like 8 or like 6 solar masses, something like this. You will get carbon oxygen white dwarfs. And then finally, and again, they basically go up to about 1.1 solar masses. And then above that, you get oxygen neon white dwarfs. And the reason why these happen is because it turns out some stars, which are of the order of 8 solar masses, maybe a little bit more, a little less, they actually start to burn carbon as well. So they turn the carbon into neon, and they undergo something called a super AGB phase, which is notoriously hard to model. And then either you can get an oxygen neon white dwarf, or it can blow up in an event called an electron capture supernova. And then more stars, massive stars than that, will blow up or like direct collapse and then not make a white dwarf. So uninteresting. Um, and those things are basically like oxygen neon white dwarfs are like ultra massive white dwarfs, right? Okay. White dwarfs, their cooling is regulated by the envelope, and the envelope is what you see. And it is very important to understand the envelope in white dwarfs. So here's a typical white dwarf. I will say typical, in quotes, because there's some diversity and also a lot of uncertainty. So you should think about a normal white dwarf as being about 0.6 solar masses and made of CO. That's something like what the sun is going to be, maybe, yeah, a little bit different. And then there's a little shell on top of helium, which is about 10 to the minus 2 solar masses. So it's like not that much, but it is still like substantial. And then there's even less hydrogen. So like a typical value to assume is 10 to the minus 4, but there's substantial evidence that actually is probably less than that in many white dwarfs. Like it's not something you can directly measure, so this kind of sucks. Okay.
Why?
Well, I think it's because like the winds basically take off most of
So
of that stuff.
I would say if some core popped out from the center of the star, like still outer layers mostly hydrogen. But that ratio looks like there is a very particular physical mechanism selectively blowing out hydrogen so well.
No, but it's okay actually, right? Because the way this works is that these things are produced typically by a thermally pulsating AGB star. So what's happening is you're burning hydrogen in an envelope, in the base of an envelope. You accumulate some helium, and then that kind of like accumulates and it blows up. And then you basically as you pulse, you're like kicking off some more material. And then at some point, your hydrogen becomes low enough that you can't have an envelope anymore.
The temperature is kept high enough to process that it's burning all the time.
Yeah, it basically has to, because if you have sufficiently large amount of hydrogen, then it has to, in order to maintain hydrostatic equilibrium, like inflate into an envelope.
If during this process, if it's supposed this core cools down really fast, then we can still have some piled up hydrogen outside of it.
Yeah. I mean, like I think in principle, if you really like snapped your fingers like God and turned it into absolute zero, then it wouldn't be burning. And you could have like degeneracy supported hydrogen if you want, but that's not really what happens like in real life. Like even if the core is degenerate, and it is degenerate in this case, even if it were cold, like the models that I've run for my previous paper, in order to have like an inert core with some burning species on top of it, you need to inflate into an envelope. Anyways, so it turns out that 10 to the minus 4 is like a guess. Okay, it's kind of like the max that you can have almost, but there's substantial evidence that many white dwarfs have like really small amount of hydrogen on them. Like I'm talking like 10 to the minus 10 or 10 to the minus 14. And the way you know that is it turns out that white dwarfs, like they have convective zones that grow over time. I'll talk about this in a second. Wow, this is really gonna take a lot of time, Dan. Anyway, so and because the convection zone grows over time, like some of the hydrogen can get mixed in. And then like you can see like the number of white dwarfs with visible hydrogen like going down over time. And you know how thick the convection zone is supposed to be in it, and you can work out things like this. Like many white dwarfs have very little amount of hydrogen. There are a lot of classifications of like spectral classifications of white dwarfs. The most white dwarfs are something called DAs. D means degenerate, and A is like kind of like an analogy with like, OBA, FGKM, classification. DA means you have like hydrogen lines. So like here's a picture of that. And DBs are like most of the rest of them, and they're like helium atmosphere, right? So like it's kind of like not really known, like I think super well what sets how much hydrogen you have. But one point is that you might be able to have like a late shell flash in the thermally pulsating AGB star. that like kicks off the last bit of hydrogen. Anyways, there's some diversity in this. And then there are kind of like other miscellaneous classes based off of like spectroscopy. Like you might see no emission lines, you might see ionized helium for the hot white dwarfs. You might see carbon, or you might see metals. And then there are some other things you can kind of append to the end, which describe things like, is it variable, or does it have a magnetic field or something like that. And then like I mentioned this before, but also when they get cool enough, and cool is relative to their surface composition, they develop a thick convective zone, and thick in this case means like 10 to the minus 12 solar masses, so still like very small. So you can see like this is for a hydrogen atmosphere white dwarf, about 12,000 Kelvin. They start to develop a pretty thick convective zone. And this is basically set by like the partial ionization zone of that species. So for helium atmosphere white dwarfs, it happens at a larger temperature, like maybe 30,000 Kelvin. Yeah.
Why do they set the axis like that?
With this one?
The temperature is decreasing for large X, and also
Oh, yeah.
mass is decreasing for
Neutron star guys do this too. Everything's upside down. I
Yeah.
don't know why.
That's yeah. I mean, I guess in this case, like you should kind of imagine this up here is like the surface of the white dwarf, like this equals negative infinity. So this is like the convective zone getting deeper, and of evolution to the right because it's cooling. And this is the same like direction of the temperature, effective temperature, as on an HR diagram. This is how we're used to looking at it. Sorry. This is what happens when you have to have fun when you're doing non-relativistic physics. So also there are some weird exotica that I'll just briefly mention. There are some white dwarfs. The first one I think is called Janus and was discovered by Lara Kayatsa, who's a postdoc here, that have like they have hydrogen atmosphere, and then they rotate around, and then they have a helium atmosphere. And that may be due to something related to like magnetism. Okay, but I won't talk so much about it. But there's like weird stuff like that can happen. This is a subject that I had to figure out, which I didn't know so much about. So please don't ask that much about it. So one thing is that white dwarfs have a very high surface gravity. That means for like normal temperature white dwarfs, like not super hot ones, if I stick metals on it, they just sink, right? And the sinking time depends on the kind of white dwarf, but it can be like days to like thousands of years to like maybe millions of years at latest, at longest for like the hotter white dwarfs. And therefore, if you see a white dwarf that has like metal lines or something, that means it has to have eaten something very recently. Like it can't have started off with that because it would be gone. And so here's an example of like a disk. And also like one thing is you can also detect disks in white dwarfs. And you can do that by seeing like a bump in the infrared, because white dwarfs are like bright, but they're bright, they're hot and they're not very big, so they can be outshone by a disk in the infrared. So you can see an example of that. And if a white dwarf has a disk, that usually means that it's also polluted, but not vice versa. So some white dwarfs that are polluted don't have disks. And it's claimed by this review that disrupted asteroids are probably the reason why this happens most of the time. Also, there's a cool technique called Doppler tomography where you can kind of image the disk in velocity space. And I don't have so much time to say how this works, but basically you have if you have an emission line and you have like a system which is rotating around, different parts of the emission line, different parts of the disk are blue and red shifted differently with respect to you. And so you can like take the evolving shape of the emission line and map it back into like a map in velocity space of this structure. This is like a famous result by Tom Marsh, and it's done all the time for white dwarfs. So this is kind of fun. They also have planets. I won't talk so much about it because I don't know so much about it, but there are basically of order a few planets known, 4 major ones. There's a neutron star over there. And then like, all of this other stuff, like there's like this transiting like asteroid thing. Anyways, so there are some white dwarfs known around on some planets known around white dwarfs, and you should bear in mind that these are weird because white dwarfs like were stars, right? So they used to be a lot bigger. So how are there like planets and stuff around them is like kind of mysterious. Yeah, sometimes it can be dynamics or some other thing. I don't know. I don't know so much about it, and I don't think that it's known. Yeah. White dwarfs can merge. That's fun. And there's a lot of diverse outcomes. There's a big diversity of outcomes that can happen when they merge. So here's what some people in my orbit affectionately call the Shen diagram, because there's a guy named Ken Shen at Berkeley who every time he publishes a paper makes a different version of this based off of his new understanding of what happens when white dwarfs merge. So here's one white dwarf, and here's another white dwarf, and then here's like every outcome that it may be possible, from like something blowing up to like something, to like something I'll talk about in a second, to like helium burning star. Like this is a really big diversity of outcomes. So you can merge two helium white dwarfs and get a helium main sequence star called an SDB. You can merge two carbon oxygen white dwarfs, and that thing can either become another white dwarf or blow up or turn into like an oxygen neon or whatever. You can have white dwarfs that, like oxygen neon white dwarfs, I think the people now think that if they gain mass, they undergo something called an accretion-induced collapse or a merger-induced collapse, where basically they just turn into a neutron star. And that's sort of set by like the competition between nuclear reactions and some other thing. And that process is kind of fashionable and important right now, because it turns out that certain processes like fast radio bursts require like young things like magnetars. They're basically like very young neutron stars. And those things have been seen in globular clusters in other galaxies. And globular clusters are like 10 billion years old. And so you need to make like a young neutron star in this very old population of stars. And one way to do it is to like merge white dwarfs. Okay. One of the fun outcomes I think is cool is if you merge a helium white dwarf with a CO, you can have a carbon oxygen core that doesn't do anything, and then like a helium burning envelope and no hydrogen. So you basically have something like a red giant, but all the elements are shifted down. And they appear as yellow supergiants. They have a lot of dust production because there's a lot of carbon in these stars. They also pulsate, so you can ask Viraj about this. He has some papers. And there are probably like a few thousand in the galaxy, of which approximately like 1,000 have been discovered by Viraj, or at least put in a catalog. Also, white dwarfs can merge with other objects like helium white dwarfs or other things, and I have a paper about this, which I won't talk that much about. One fun object which people are kind of interested in right now is called PA30. It's named after this guy named Patchik, and he's an amateur, and this is the 30th thing he found. And it turns out it looks kind of like a planetary nebula, but it's actually like a merger remnant, probably. So this is like two white dwarfs merged in 1181, and some Japanese astronomers saw it and wrote about it and said it was as bright as Saturn. And we now think this was probably what we would call a 1AX supernova. So like the star doesn't blow up, but it does something like less than blowing up, but it's still a transient. And this thing is, it's weird. It has like these weird, like sharp, filament features that we can't explain yet. And then there's like a central star in the middle that's like obscured to the point where we can't really tell what it is. And like the nature of this thing is like not fully explained. So you can ask Daichi about it. He's been thinking about it. So that white dwarfs can blow up. Why do they blow up instead of stably burn? Like, this is because of nuclear reactions. They blow up because of nuclear reactions, but why doesn't something like the sun blow up? Well, white dwarfs are degenerate, right? So that means that P goes as rho to the 5/3, or more precisely, or less precisely, P doesn't depend on temperature very much, right? So usually stars, when they burn something, they release energy, and the energy increases the temperature, and then the pressure goes up, and then basically like the star starts burning, and then it like puffs up, and then it's like burns less, right? It regulates itself. White dwarfs do not do that, right? Because when they increase temperature, the pressure doesn't go up, but the temperature went up. And if the temperature goes up, it turns out that the burning rate goes as the temperature to like a big power, like T to the 10 or T to the 90 or something. And so basically, like if you start burning, then the star could blow up, basically. These events are blowing up white dwarfs. That's called a type 1A supernova, and these are famous kinds of standard candles, right? Because like it's claimed that they have very similar brightness as each other, although like there's trouble in paradise because there's a big diversity of these things. How do you blow up white dwarfs? This is not fully understood, but basically there are two main kind of categories of channels. One's called single degenerate, where you basically have like a normal star accrete mass into a white dwarf. But there are some issues with this. So if the white dwarf is accreting mass too slowly, that mass doesn't it kind of like accumulates and then it blows up in novae events. And then it does like I think there's evidence that basically you don't keep a lot of the mass that you accreted. If you gain mass too fast, you inflate into a red giant thing, and then you don't really keep that mass. There's like a wind that can remove it. And you really can only gain mass if you're in like this narrow range of mass accretion rates between like 10 to the minus 8 or 10 to the minus 6. Then there's double degenerate. Yes.
Like the white burst blow up.
Yeah.
Well, that, okay, so the statement that the burning rate gets higher for higher temperature is still true for normal stars.
Yes, that's true. That's true.
That because the portion of the pressure that coming from degenerate is larger. Could that it could have been just like we can just wait until the temperature gets high enough. And then you can still imagine white dwarfs just getting hot and just try to puff if the reaction just gets enough fierce and then sort of regulate itself.
Yeah. So of course, eventually the EOS will enter a regime where the pressure actually goes up with temperature, but like that can take some time. Yeah.
So what exactly differentiates between the stars that can be self-regulated by this process and just stars that can.
Well, I will say like the criterion people typically use for does the white dwarf blow up is basically if the like the nuclear burning time scale, is comparable to the dynamical time, because then like material can't kind of move the energy away. Then it can accumulate and then do something dynamical. That's basically the criterion you can use.
There's not enough time for the heat to be distributed.
Right, by advection or something.
Then why does it just blow or say just partially disrupted?
That's a good question. It's usually people will say 1As don't leave behind anything. I don't really know exactly why, but yeah, they don't leave behind anything. The other scenario is double degenerates, which is basically two interacting white dwarfs. So like there's now a story about I mentioned there's like some layer of helium on top of the white dwarf, and there are many scenarios where one white dwarf transfers mass into the other. The helium blows up first and then like sends a shock wave into the CO, and then the CO blows up. And just to make this clear, the white dwarf in the first scenario is imagined to blow up when it reaches Chandrasekhar, but the one on the right doesn't have to be anything like Chandrasekhar. In fact, more massive white dwarfs are harder to blow up. Like very massive white dwarfs are hard to blow up because they have like a thin layer of helium, and so it doesn't, there's not much helium to like do this process. And some of the progenitors can be imagined to be things like AMCVNs, which are helium white dwarfs and COs. Yeah. Anyways, I'll try and show you everything, even if I can't talk about it. So when white dwarfs blow up, if they have a companion, that companion can go flying. There is a class of objects now called the D6 stars. They're called, which stands for dynamically driven double degenerate double detonation. So so Kareem has found several of these things, and some other people have found some of these things. They're basically like kind of like inflated white dwarf looking things. They look like they're flying out of the solar system, flying out of the galaxy faster than the escape velocity. And they look like, based off of like, if you trace them back to the disk, they should be like 100,000 or like a few million years. But it's kind of hard to imagine how that happens, because like if you run a supernova shock into a white dwarf, it's hard to make it stay inflated for that long. But see this other paper, which is trying to think about it right now. I'll skip this. Okay, this is going to be painful. So white dwarfs gain mass from companions. This sort of object is colloquially called a cataclysmic variable, even though in the past it referred to anything that looked like it blew up or like did anything cataclysmic. Nowadays, we think of this as a accreting white dwarf. It's typically some low mass white dwarf, and it's basically like the white dwarf accumulates mass on its surface, then the mass like blows up, and then it kind of puffs up. It doesn't like blow up the white dwarf, it just kind of blows off the hydrogen. These events are called novae, and they happen more often for more massive white dwarfs, such as T Corpor, which is like a very massive white dwarf. There is some stuff related to, so it turns out that there's a thing called a period gap. So there are missing white dwarfs in this range, 2 to 3 hours. And then there's a period minimum corresponding to when the donor is out of thermal equilibrium. So this is about 80 minutes. So these are like important features in the CV distribution, but they're not well understood. They're not understood that well. And the stories about them are kind of like this trouble in paradise. There are also magnetic CVs. So there are situations where the white dwarf is magnetic and it disrupts the inside of a disk, accretion disk, which is called an intermediate polar, and sometimes it disrupts the entire disk. And the magnetic field is strong enough that the material that comes in is channeled along the field line and like until it hits the surface, like on a pole. And these are pretty interesting, and I don't have time to talk about them. And then there are all these other words because this field is very big. There's also a class of object called white dwarf pulsars. The prototype is called AR-SCO. There are like only a few known. I think like more recently there are some more papers, but this is the main one, AR-SCO. It looks like an M dwarf. There's probably a white dwarf in there, and it basically pulses in the same way that a neutron star pulsar would pulse, but like once every few minutes. And it looks like the spin down of the white dwarf, which you can measure somehow in the variability, seems compatible with the energy coming out of the SED.
That's actually, that has the best. The continuously discussing that community, that the pointing flux coming out from this rotating magnetized object is not an
Okay. Yeah.
So I don't know.
Okay, controversial. It's certainly not well understood. Okay, we can put it at that. And then there's some other objects. This is the main other one.
Maybe the paper was just simply quoted the blocks, but
Yeah. It's an order of magnitude argument at this point. There's also a story about how like why is it that like there are so many magnetic CVs like polars and not that many pulsars? There's some story about this which may or may not be right. I'm not going to talk about it. There's also something called an LPT. There's an L missing, but you can ask Tony about it because I don't know anything about it, and it's this whole can of worms. Maybe similar. White dwarfs can be magnetic. Magnetic usually refers to like a mega Gauss, but that's only Zeeman splitting. That's just like you see a spectrum and it has multiple lines where there should be one. But it turns out that you can measure lower magnetic fields than that with something called spectropolarimetry, because it turns out those lines are polarized differently. So if you look at that thing in different polarizations, even if the lines overlap, the residual and the polarizations can still make a little like bump feature. So you can measure like things down to, I will say like, I'll quote like 10 kilogauss or something. They can also have spots, which are presumably due to magnetic fields, even if you can't measure them. And they can often be in a non-linear regime of the Zeeman splitting. So you have to like make a diagram like this, like figure out what magnetic field it has. It's now known that like magnetic fields are most common in white dwarfs, which are less than about the crystallization temperature. I'll mention that very briefly later. And then ultramassive white dwarfs are more likely to be magnetic, probably because they merge, and then there's some reason why that makes a magnetic field. There's a class of objects called a hot subdwarf, which is like basically a helium burning star, many of which should originate from helium white dwarf mergers. But then it turns out that most of them are not magnetic, and those that are magnetic are like in this weird class called SDO. And we don't know why these objects are like preferentially not magnetic. So that's an open question. White dwarfs can be ultramassive. I mentioned that single star evolution can make 1.1 solar mass oxygen neon white dwarfs, but not really COs. Mergers may be able to make COs that are that massive, or maybe not. About half of ultramassive white dwarfs may be merger remnants, just because you can look at them and some of them are like very magnetic, some of them like are like moving fast, some of them have like fast rotation. You can like make an inference that an order unity fraction of them should be mergers. Ilaria has a fun paper where she discovered a white dwarf as small as the moon in size, which means it's very massive, so close to Chandrasekhar. White dwarfs crystallize. Okay, so basically they're made of carbon and oxygen or oxygen and neon. And it turns out that when the white dwarf's cool enough, the Coulomb forces are large enough that they can do chemistry basically. And what happens in the case of CO is that the oxygen-rich material freezes and squeezes out some carbon-rich liquid, and the carbon-rich liquid can like rise and cause some mixing. And oxygen neon does the same thing, but at higher temperature. That can cause a dynamo, maybe. That was suggested in 2017, but probably not, because the mixing is actually very slow. And over time, people have realized that it's even slower than they thought. But it's still possible so this is sort of suggested to be an explanation for why cooler white dwarfs are more magnetic. But even if the convective motions can't make a magnetic field, they can still like mix out a magnetic field in the deep interior of the white dwarf just because it's mixing. There are also objects called the Q branch and something called the Q branch. So you can see like this is what the white dwarf curve looks like. This is what like the HR diagram looks like for white dwarfs. You can see that like basically white dwarfs start off on the top left and then cool to the bottom right. And the ones that are below the curve are more massive. So you can see there's like a little bit of overdensity over here corresponding to crystallization. This is basically like a white dwarf reaches that temperature and then it releases energy and then it stays around over there. But it turns out that this overdensity is too much to be accommodated by carbon-oxygen cooling, the carbon-oxygen phase transition, right? And first of all, these are ultramassive white dwarfs, but this is happening at the carbon-oxygen transition, not at the oxygen-neon transition. So for some reason, these are carbon-oxygen white dwarfs probably. And second of all, the overdensity is too high. So it's been suggested that maybe the liquid is actually heavier because in these white dwarfs, they're enhanced in neon-22. Neon-22 is like heavier species, and so it turns out it's preferentially in the liquid phase. And so if there's enough neon-22, the liquid's heavier, and the solids, the white dwarf doesn't crystallize like per se, doesn't make a crystal core. The crystals actually rise, and then they go really high up in the white dwarf, and then they melt. And then that efficiently turns potential energy into heating. So that's the current story about these things. But you need to have a lot of neon-22, so maybe the metallicity in the environments that made the stars was high, or maybe it's some kind of merger. And I won't talk that much about it. Magnesium-26 also can be made in stars like this, in the progenitors, and that can also participate in this distillation process. Okay, white dwarfs sometimes have emission lines. White dwarfs should not have emission lines, but they have them anyway sometimes. The reason why white dwarfs shouldn't have emission lines is because the reason why you have emission lines is because there's something in front of you, like on the outer layers of the white dwarf that's hot, and the stuff that's behind it is cooler, right? Because the way that lines work is you look at the star and then you see like if the star is more opaque, then you see the outer layers, and if the star is less opaque, you see the inner layers. And the star is more opaque at atomic transition. So basically, you see emission lines when the atmosphere is like hotter than the photosphere. And white dwarfs should not be able to do that because white dwarfs are just like sitting there doing nothing. So how is it that the atmosphere is hotter than the interior? This is the original object of this has been known for like 40 years, and it's called GD358. It's in the DAHE class. And people used to think that it's because there's a planet, like a conducting planet within the Alfvén radius, and maybe there's some star-planet interaction. So this is called the unipolar inductor. But it turns out that last year, or 2 years ago now, they discovered like 24 of them. So like gradually they accumulate like of order a few of these objects and like learn stuff about them. But now there are like 24 of them. They have some common properties. They're rapidly rotating preferentially. They're slightly more massive. They're at 0.8 solar masses with some scatter. And the main feature is that they're almost all the same temperature, or they're basically like all consistent with being the same temperature and consistent with the temperature of carbon-oxygen crystallization. So that's kind of interesting. And we have a little story in this paper about how we think that happened. We think these things might be neon-22 enriched, and we have some story for how that turns into emission line power. But I don't have time to talk about it. And the last thing is, oh, actually, is this the last thing? Okay, no. So the last category of things I want to talk about is something dear to my heart, which is astroseismology. So white dwarfs pulsate. White dwarfs pulsate because there's something that drives it. That can be some mixture of like the Kappa mechanism, which is something that operates in things like Cepheids or Delta Scutis. Or it could be something cooler, like convective driving, like in the sun, which is something that you can see papers by people like Brickhill or like Peter Goldreich and Yanshin Wu wrote like several papers in either order. And basically, they pulsate usually when the surface is like the correct temperature to be consistent with a partial ionization zone. So it probably has to do with like convection, why they're being driven. And here's what's called a Kiel diagram, which is kind of like log G on the up and down in the inverted axis, and then temperature on the bottom also in inverted axis, things evolving from left to right. So you can see like there are these pre-white dwarfs, which are like very big inflated things that like including things which are in planetary nebulae. And then they kind of go down here and then they cross some instability strips. And the main one here is the ZZ SETI strip, which are the DA white dwarfs corresponding to like hydrogen atmosphere. But there are also helium atmosphere white dwarfs called V777 HERS, also DBVs. And then there's now a class of things called ELMs, which are like extremely low mass white dwarfs, which are like 0.15 solar masses, and they can also pulsate. And then there are also things called pre-ELMs, which are like ELMs, but like I guess they haven't thermally relaxed as much. There are pulsators in cataclysmic variables called GW libs, and then there's like all sorts of other stuff. They're gravity modes. Okay, so white dwarfs have a dynamical time which is very short, like seconds or like tens of seconds. But the white dwarfs typically pulsate somewhere between like hundreds of seconds and thousands of seconds, like mostly less than about 1400 seconds. But ELMs can pulsate for like thousands of seconds. Because they're gravity modes, the modes are spaced apart in the period spacing, in equally in period. Um, and but like the pulsations are actually like very concentrated near the outer layers, and so there are actually like a lot of non-ideal effects which depart from this. And if you do this sort of analysis, you can measure things like rotational splitting, so like rotation within the white dwarf, maybe even like differential rotation, it's claimed. And also, you can see like nonlinearity in the light curve. So there are like combination frequencies in the light curve. It turns out that if you watch white dwarfs for long enough, their frequencies, especially the low frequency ones, the modes will like actually drift around in frequency. And there was for this white dwarf GD358, which is also the prototype. It's also called B777 HER. It had this one observation where like randomly on one day, like two modes like dominated the entire light curve. Like they just ate all the energy in the other modes and then they dominated the light curve. And then after that, the asymmetries in the rotational triplets moved around. And so like this is like a whole thing. Like some people like spend all of their time caring about this white dwarf and like what's going on with it. There are also some ultramassive white dwarfs which pulsate, including one that was just discovered that has 19 modes, which is the
19?
most 19.
Oh.
Yeah. So this is like precision science. You measure these things to like few hundreds of a microhertz, and then this one had 19 of those, which was great. The last thing I want to say, which is something that I work on, is it turns out that if you have a magnetic field that can modify where the modes are in a distinctive way, it can make the rotational multiplet like asymmetric. That has been claimed to be discovered in this white dwarf by Don Wingett and like his collaboration, the Whole Earth Telescope. So these people, what they do is like they kind of station like observatories all over the Earth, and then they like watch a white dwarf, like try and watch it like 24/7 basically, and that's the Whole Earth Telescope. Actually, there's a line from a paper where they're like, this is like a very difficult undertaking. Like sometimes people get stabbed, and then there's a citation. So, so it's this used to be very hard to do. This white dwarf another person has claimed that this white dwarf may have what's called an oblique pulsation, which is like the magnetic field misaligns the pulsation from the rotation axis, and then it like appears as multiple different peaks. And so you can see that if you try and fit an inclination to different observations, it appears to be sinusoidal inclination of the pulsation. And then I have a paper about this as well, where it turns out that we think that you're basically sensitive to the near surface magnetic field with seismology, and you can put very strong constraints based off of the fact that you're seeing modes or that you're seeing rotational multiplets which are evenly spaced. Okay, that's the end. That was a lot. I don't expect you to remember all of that. I mean, I'm not a teacher or anything, but I want to communicate. Hopefully, I want to communicate here that there's like so much in this field. On the one hand, they're like the matter is less exotic than neutron stars, but on the other hand, the physics in white dwarfs is a lot more well understood, but still very much less well understood because you have a handle to maybe try and understand what's going on in them, but there's like such a diversity of stuff that can happen in them, and this is by no means exhaustive. Okay, thanks.